Hey everyone, Katrina here, and today we're going to talk about defective eigenvalues. Be sure to subscribe for more videos like this. Okay, so I have some previous videos out which talk about algebraic and geometric multiplicity. These videos are core to understanding whether eigenvalues are defective or not, because their very definition relies on both their algebraic and geometric multiplicity. So if we look at the definition of a defective eigenvalue, this is what we get. So when the geometric multiplicity of a repeated eigenvalue is strictly less, so not less than or equal to, but strictly less than its algebraic multiplicity, then the eigenvalue is said to be defective. So the geometric multiplicity tells us how many, so that's the number of independent eigenvectors that are associated with an eigenvalue. And the algebraic multiplicity is the number of times our eigenvalue lambda appears as the root of our characteristic polynomial. So if we have a repeated eigenvalue, so let's say that its algebraic multiplicity equals to 2, and its geometric multiplicity is less, meaning that it equals to 1, for example, that means that that eigenvalue is defective and our matrix is not diagonalizable. So if we look at an example, so I showed how to solve this in detail in a previous video, but for the sake of this understanding of defective eigenvalues, if we consider our matrix A, which equals to 1, 0, negative 1, 1, and we find the characteristic polynomial, we see that we're looking for the determinant of A minus lambda I, set that equal to 0. Here we get 1 minus lambda times 1 minus lambda minus 0 times 1 equals to 0. So in this case, we can see that our lambda 1 equals to 1 and our lambda 2 equals to 1. So that means that lambda 1 equals to lambda 2, which equals to 1. Therefore, we have a repeated eigenvalue. So that tells us that the algebraic multiplicity equals to 2. Okay? But then in this case, I'm going to fast forward and show you how many eigenvectors we have associated with it. If you want the full example, be sure to check out the other video where I walk through this step by step. But here we're going to use the definition to find eigenvectors such that AV equals to lambda V, where this V here is our eigenvector and our lambda here is our eigenvalue. So if we follow this definition, we actually get that our V, our eigenvector, is equal to, let's say, k, which is any scalar, multiplied by 0, 1. So k is any scalar. So this tells us that we have one independent eigenvector associated with our eigenvalue. That means that the eigenspace has a dimension equal to 1. So both of these things tell us that the geometric multiplicity equals to 1. So in this example, we see that the algebraic multiplicity equals to 2 and the geometric multiplicity equals to 1. Therefore, the algebraic multiplicity is strictly greater, or you can say it the other way, the geometric multiplicity is strictly less than the algebraic multiplicity, and that tells us that our eigenvalue is defective. So I just wanted to make this video so that you understand the terminology of defective eigenvalue. You might hear the other jargon about the multiplicity being thrown around, whether the matrix is diagonalizable possible or not, but defective is also used in some cases. So I just wanted you to have a thorough understanding that if someone says, oh, this eigenvalue is defective, they're literally just saying that the algebraic multiplicity is strictly greater than the geometric multiplicity. Anyways, I hope you enjoyed that quick lesson. If you have any questions about this topic, please feel free to write a comment. I'll get back to you as soon as possible, and definitely check out the playlist because I cover so much about eigenvalues, eigenvectors, and linear algebra here. And please subscribe for more videos. I look forward to seeing you next time.